Dear students, welcome to the third session of our Chapter 3 Classification of Elements and the Periodicity in Their Properties. Today we will deal with the topic Periodic Properties. Periodic trends in physical properties first we will discuss. In that, shielding effect and effective nuclear charge is there, atomic radius, ionic radius, ionization enthalpy, electron gain enthalpy, and electron negativity is there. And regarding the periodic trends in chemical properties, we have to deal with periodicity of valence or oxidation states, anomalous properties of the second period elements, and the chemical reactivity. So these all periodic trends in the periodic table we have to learn. Now let's see what you mean by shielding effect and the effective nuclear charge. The decrease in nuclear charge. Decrease in nuclear charge is otherwise said to be nuclear force of attraction on the outermost shell electrons and due to repulsion caused by the inner shell electron is known as shielding effect of inner shell or intervening electrons on the outer shell electron. So in short, we can say there's a decrease in the nuclear charge on the outermost shell due to the repulsion of the inner electrons, and that effect is said to be shielding effect. So if we are having a number of orbits, the outermost electron will be having a very less nuclear charge. Why? Because the inner electrons are pulled towards the nucleus, or these inner electrons will be having some repulsion towards the outer. So what happens? The nuclear charge decreases. Due to the shielding effect, the nuclear charge is lowered on the outermost shell electrons. And that's why the net nuclear charge acting on outermost shell electron is said to be effective nuclear charge. So we already said that the outermost electron or outermost shell electrons are experiencing a low shielding effect. So what net nuclear charge they are having on the outermost shell electrons, it is said to be effective nuclear charge, and it is denoted by Z star asterisk or Z if EFF we are writing. We are denoting with this symbol Z asterisk or ZEFF. This is effective nuclear charge. And here we can give an explanation for this definition, that is, or the formula, that is Z star is equal to Z minus sigma, where this Z is the nuclear charge, that is the atomic number we can use, and sigma is the shielding constant or the screening constant. It is a measure of shielding effect. If we see the trend of effective nuclear charge ENC in the periodic table along a period, it increases rapidly along a period, that is 0.65 per next group will be there. That is, if we are taking the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon, if we take the second period, the effective nuclear charge is, the calculated value is 1.3, 1.95, 2.6, 3.3, 3.9, 4.6, 5.2, 5.9, and these all increases rapidly along a period with the increase of 0.65 per next group. That is 1.3 plus 0.65 gives you 1.95. Like that, the increase is there for the next element in the particular period. In a group, effective nuclear charge increases slowly along a group. So, what is the difference? One is increasing rapidly, the next one along the group it increases slowly, and that increase is like this: hydrogen, lithium, sodium, potassium, rubidium, cesium. This is the first group. In that, the effective nuclear charge is 1, 1.3, 2.3, 2.2 itself, 2.2, 2.2 itself. So that's a slow increase only, very slow increase. We can say it is like going down the group, it becomes a constant also. So the effective nuclear charge increases along the period rapidly, and in a group also there's a slow increase while we are going the first group or second group, whatever it is. Next periodic trend is the atomic radius. In this, we are having three types of radius, that is metallic radius, covalent radius, and ionic radius. When we talk about the metallic radius, it is the distance between the nuclei of nearest neighbors in the solid. Let's see one example. Here we have taken two metals and the distance between the two nuclei is said to be the metallic radius and it is given as 186 picometer. So from the center part of the one metal to the second center part of the metal is said to be the distance as metallic radius. And the next one is the covalent radius. The word covalent represents what the sharing of electrons done. When we are taking for the metals, we can't say the covalent nature it is having. So we are taking here the non-metallic element. And here the distance between the two nuclei or the nearest neighbors in the solid is said to be what? The covalent radius. And we have here taken the example of chlorine. When we have here two chlorine atoms, they will share the electrons with each other making a covalent bond. So the two atoms, that is chlorine's atom, and this chlorine's atom is having a center part or the nucleus is there. The distance between them is said to be covalent radius. And the last one is the ionic radius of the element, which is the distance between the nuclei of the neighboring cation and the anion. When we talk about anionic or cationic, we should say that one cation and one anion should be there to make a molecule. So if we are having a NaCl, in that Na plus and Cl minus ions are there. Sodium cation and chlorine anion is there. So the center part of the sodium plus ion to Cl minus center part is the distance which is named as ionic radius of the element. And the trend when we see in a group, the atomic radius increases down the group because along a group from top to bottom when we talk, n increases. What is n? The number of orbit increases as well as the z increases. What is the z? It is what? Z is the nuclear charge. And there's no dramatic increase in the effective nuclear charge. Almost it remains a constant. Now, along a period, the atomic radius decreases with the increase in atomic number. When you go along the period, what happens? The atomic number increases. And of course, what happened? The atomic radius will decrease. And the reason for this one is because the n or the number of shells remain constant. The same shell is there for the period. How many shells it is there? The same will be there for the whole elements in that same period. Then Z increases by 1 unit. That is, nuclear charge will be increased by 1 in the case of period. Then, what about the effective nuclear charge? Effective nuclear charge will be increased by 0.65 unit. Each and every group it is like that in along the period. The electrons are pulled close to the nucleus by the increased effective nuclear charge. So this is the reason why the atomic radius decreases in a period. And in the group it increases going down the group because the number of shells are increased. So of course the size of the atom will increase. Next periodic trend is the ionic radii. When we talk about the ionic radii, there comes the anion and the cation. Now, we know that the anions are larger than their parent atom. This sentence you have to clarify with the explanation. That is, because of the addition of one more electron. Anions means what? They can accept the electrons. So, when more than one or one electron is accepted by the atom, it would become anion and it would result in the increased repulsion among the electrons and there will be a decrease in effective nuclear charge. That's why compared to the parents the anions are larger. And in the case of cations, all the cations are smaller than their parent atom. And the reason for that one is because when you take the cation, it loses the electron. there will be few electrons or few less electrons compared to the parent, and its nuclear charge remain the same because nuclear charge is not going to change. The atomic number that sodium means 11 electrons are there, so the nuclear charge is there. But when the positive charge coming, what happens, the electrons number is less there, and hence what happens, the effective nuclear charge will be greater in the case of cation compared to the parent atom. So that is the reason why the cations are smaller and why the anions are larger with their parents. Now we will talk about the term isoelectronic species. What do you mean by isoelectronic species? Iso means the same. The word electronic means electrons. So same number of electrons if it is coming, we name it as isoelectronic species. The atoms and the ions which contain the same number of electrons are said to be isoelectronic species. And we are having here some examples like F minus, fluorine minus. Fluorine is having 9 electrons. If you put the minus sign, that means it gains 1 electron, making it 10. Sodium plus. Sodium plus means 11 electrons were there, 1 is lost from there, that means again 10 electrons. Mg2 plus, 12 electrons are there in the magnesium. When you lose 2 electrons, it becomes 10. So all are having the number of electrons equals 10. So this is all what isoelectronic species with the number of electrons 10. The size of isoelectronic species decreases with the increase in nuclear charge. This sentence we have to remember, that is, the size of electronic species decreases with increase in nuclear charge. That is, the order will be O2 minus greater than F minus greater than neon greater than Na plus greater than Mg2 plus greater than Al3 plus. So, according to the increase in nuclear charge, the size of the isoelectronic species decreases. With this example, you can understand the size, how it is decreasing for the case of isoelectronic. Now here is a graph which is plotted against the atomic number and the atomic radius. But here, the along the period, the graph is plotted. The second period, third period, fourth period, fifth and sixth period, it is mentioned here. Like lithium to fluorine, sodium to chlorine, potassium to bromine, rubidium to iodine, cesium to the last element. So this is what along the period. And when we learnt the along the period, what happens to the atomic radius? It decreases. It decreases. So you can see here in the graph all the groups plot when you are plotting, it is having a decrease. So along the group, if you plot the graph, atomic number versus atomic radius, there will be increase. So it's clear that you can plot the graph for both the cases. Now one more thing we have to note, that is the metallic radii in the third row of D block element. It will be similar to the second row of D block, and that is because of the lanthanoid contraction, as the f orbitals have poor shielding effect. That is, lanthanoid contraction comes in the third row because the third row elements are separated and kept as lanthanoid series. So with this we are concluding. We'll continue in the next session.